Okay, so in this example 2.8, we are going to deal with a multi-stage problem, specifically a three-stage problem using the scenario variable formulation. So let's consider an electric energy producer with a production capacity of 120 megawatts. Okay, so the producer has two choices to buy energy, to sell energy using two contracts. Okay, so the first contract, the producer can sell up to 50 megawatts at $25 per megawatt hour, and that decision has to be made at the beginning of the 6-day period and spanning the entire 6-day period. Okay, so the time horizon for this problem is a 6-day period divided into two 3-day periods. Okay, so the first contract, the producer has to decide if buying energy using that contract at the beginning of the 6-day period. The second option is a selling contract up to 40 megawatts, selling it at $26 per megawatt hour, but it only is available for the last 3-day period. Okay, and the decision to buy energy, to sell energy using this contract has to be done before the 2nd-day period. Okay. All right. So here in this table, we summarize what we just said: the contract AB, duration, hours, price, and power cap. Okay. Also, the producer has an option to sell energy in the pool. Okay. But here we have different scenarios. Okay. So in the first 3-day period, right, the pool prices are $27 per megawatt hour with a probability of 0.4 and $23 per megawatt hour with probability of 0.6. Okay. Had the first period be with a price of $27 per megawatt hour, then in the second period, we have two chances. Either the price is $28 per megawatt hour with probability 0.4, or the price of electricity is $26 per megawatt hour with probability 0.6. Okay. Alternatively, if the price in the first period is $23 per megawatt hour, okay, then in the 2nd-day period, the prices are $24 per megawatt hour with a probability of 0.4 and $22 per megawatt hour with a probability of 0.5. Okay. So we summarize that in this table, right? We have 4 scenarios: the prices for the first period, prices for the second period, and probability. Here we're multiplying probabilities because the first factor corresponds to the probability of the first scenario. Sorry, of the first 3-day price, okay, of the first period, and these ones correspond to the probability of the second period. Okay. All right. So then we can use a tree to represent this uncertainty, right? And as we said at the beginning, this is a 3-stage problem. So at the first stage, the producer has to decide if he's going to buy energy, sell energy using contract 8, and how much energy. Okay. In the second stage, once the uncertainty realization occurs, right? Then the producer has to decide how much energy he's going to sell using contract B, right, for the rest of the period. Okay. So the decision for contract B is a future decision. Okay. So we are here and we have to decide how much energy we're going to sell using contract B for the 2nd-day period. However, for the pool scenarios, right, the ones we are placed here, we have to decide how much energy we're going to sell in the 1st-day period. Okay. Remember that there were 2 prices for the first 3-day period: 27 or 23. Okay. So we have to decide, once we are here, we have to decide how much energy we're going to sell if the price is 27 with this upper branch or 23 with this lower branch. Okay. In the third stage, okay, now we again look back and decide how much energy are we going to sell using the uncertainty, right? That is represented by these branches. So if the price in the first period is 27, we had two options for the prices of the second period, right? And they were 28, 26. If the prices in the first period are 23, the prices in the second period are 24 and 22. Okay. So this is 28, 26, 24, 22. Okay. So that's why we decide to model, the author decided to model this problem as a three-stage scenario. Okay. In the first stage, decide how much energy we'll sell with using contract A. Second stage, decide how much energy we will sell using contract B, and decide how much energy we are going to sell into the pool for the first 3-day period. And in the third stage, we have to decide how much energy we're going to sell in the second day period, in the second period. Okay. So this is a maximization problem. We want to maximize profit function in this case. For examples 2.6 and 7, they were a cost function. So in this case, it's a profit function, right? We have the probabilities for all the scenarios, 72 hours, right? Because that corresponds to the number of hours in 3 days for one period. Then we have the cost, sorry, the profit for each production of energy. So in the first term, we have two, because for the pool contract, remember that this contract A, sorry, not the pool contract, for the contract A, right? The number of hours was 144. So that's why we multiply 72 times 2, that we have 144. 25 is the price of energy using contract A. Okay. Then we have the term for the price of contract B, right? Then we have the price for this is the first period, right? For each of the scenarios. We have 27 and 23. And then we have the second period for all the scenarios and each corresponding cost. Okay. Notice that the variables are 4 variables, okay, for the price, for the power of contract A for the 4 different scenarios. Same for contract B, same for first period, same for second period, because we are modeling this problem using a scenario-based approach. Okay, so each variable corresponds to each scenario. So subject to, these are the cap constraints. So remember that the producer can only produce 120 megawatts. So in the first period, right, we have the energy cell using contract A and the energy cell in the pool. Okay, so this has to be capped by 120 for all the 4 scenarios. So these 4 correspond to the first period. Here in the second period, we have energy cell using contract A, but we also have energy cell by contract B. Okay, and we have the pool energy cell. Okay, selling. Okay, again, this has to be capped by 120 because that's the maximum energy the producer can sell. Then we have the box constraints for the maximum power that you can sell using contract A, the maximum power you can sell using contract B, and the non-negativity constraint for all the other variables. Okay. And then we have the non-anticipativity constraints, right? So each common node, we have to make it to be equal. So for example, all the variables in this node has to be equal. All the variables in this node, okay, in this case corresponding to contract B, and to the amount of power we sell in the first period has to be equal. Okay, this has to be equal. The variables here has to be equal because they are common to other nodes. Okay, so the variables here has to be equal. Okay, and that prevents us to have, if we have different values for this, for example, here, if we have different values for different scenarios, right, then the problem is not being solved correctly, because as the book explains, right, if that happens, that means that the variables here are taking advantage of the future realizations, okay? And remember, if we are here, we don't have the information of what's going to be the price in the first period, okay? If we know the price, then the variables here will be different, but we don't want that because we don't know the future information, so all the variables here has to be equal, same for these variables here, okay? In other words, pairing nodes all the variables in pairing nodes has to be equal. So that's happened for the root node, okay? Then in the upper node, in second stage, right? The power using sold using contract B has to be equal. And for the lower node, has to happen the same, okay? Similar in the upper node, the powers sold in the pool market, right? For the first period has to be equal, and similar for the lower node. Okay, so that's explained a better way using here in the book. So now let's move on to the code. So okay, so here is example 2.8 in code. So I'm using Gurobi and Python and Jupyter Notebook for coding this problem. Okay, from the data, I have the 4 scenarios. I have this bar types, which corresponds to A, B for the 2 contracts, and T1, T2 for each of the periods. The number of days, the number of hours in 3 days is 72. I have the probabilities, right, from the table we saw, and the prices for each of the scenarios, okay? Notice that I have included the 2.25, 26, 27. If we see them over here, I'm just saving in the dictionary these values, okay? Similar for all the rows. I create the model, I add the variables, right? I'm gonna create one mega variable or one matrix of variables, okay? Indexed by the scenarios and the bar types, okay? The lower bound is 0. Type of variable is continuous. I update the model, and here I have the objective function where I do a quick sum. Okay, notice that this term or this objective function is a sum of sums, right? So we are summing these 4 terms, 1, 2, 3, sorry, and 4. And inside of each of those terms, we have a sum, which is here, 1, 2, 3, and 4. 1, 2, 3, and 4, so on, okay? So I have a quick sum, right? I'm arranging those terms in this way, right? We have the probability, the number of hours in 3 days, 72. And then I'm summing inside, right? Which is the price times the power. And I'm doing that for all types, right? Which corresponds to contract A, contract B, first period, second period, and for each of the scenarios. Okay. Then we maximize. Then we have the constraints, right? This is the constraint for the power produced in first period. Cap consists of contract A and pool, and is capped by 120 megawatt hours. Sorry, 120 megawatts. So we have for each of the scenarios, right? For contract A plus first period in the pool market, right? We have capped by 120, okay? Then we have for the second period, right? And for all of the scenarios, okay? We have the power from contract A, power from contract B, and power sold in the pool market in the second period, capped by 120. Then we have the capacity constraints. The power produced in contract A has to be less than 50. That's at most how much power you can sell using contract A. The case for contract B. And here I have the non-anticipativity constraints, right? All the variables have to be equal for first stage, for second stage, okay? And this is for first stage second stage respect to the contract, and second stage respect to the first period. I update the model and I optimize, okay? This is the profit value, okay? And here I'm visualizing the variables, okay? So this is the solution shown in the book, okay? And that's it. Thank you for watching.